Unsupervised learning techniques. Unsupervised learning techniques are essential in machine learning, especially for organizing data into meaningful groups or clusters. Unlike supervised learning, which relies on labeled data, unsupervised learning seeks to uncover hidden patterns and relationships within data without prior knowledge of the categories. This chapter explores three widely used clustering algorithms: K-means, hierarchical clustering, and DBS-CAN, as well as the powerful dimensionality reduction technique known as principal component analysis, PCA. These methods help identify trends, reveal categories, and segment data efficiently. We'll delve into each algorithm, its unique features, applications, and benefits, with a particular focus on their use in finance. K-means clustering. K-means clustering is one of the simplest and most frequently used clustering techniques. The algorithm partitions a dataset into a predetermined number of clusters, denoted by K. Each cluster is defined by its centroid, which acts as the cluster's center point. The process begins by randomly selecting K initial centroids. The algorithm then assigns each data point to the nearest centroid, forming clusters. Once the data points are assigned, the centroids are recalculated based on the average of the points within each cluster. This process continues iteratively until the centroids stop moving significantly, indicating that the clusters are well-defined and compact. K-means clustering simplicity and efficiency make it a popular choice for many applications, especially in the financial sector. For example, banks use K-means to segment customers based on their spending or investment behavior. This allows financial institutions to offer personalized services and products to different customer groups, improving customer satisfaction and loyalty. K-means also excels in market segmentation, fraud detection, and identifying patterns in large financial data sets. Hierarchical clustering. Hierarchical clustering is another widely used technique that builds a tree-like structure of clusters, known as a dendrogram. Unlike K-means, hierarchical clustering doesn't require a predetermined number of clusters. It works by progressively merging or splitting clusters based on their proximity to one another. There are two main approaches to hierarchical clustering: agglomerative and divisive. Agglomerative clustering. This bottom-up approach starts with each data point as its own cluster. Pairs of clusters are then merged based on their similarity or distance, continuing until all points are combined into one large cluster. Divisive clustering. In contrast, this top-down approach begins with all data points in a single cluster and recursively splits them into smaller clusters. Hierarchical clustering is particularly useful in exploratory data analysis, where understanding the relationships and hierarchies among data points is essential. In the financial world, hierarchical clustering is commonly used for risk profiling, where assets are grouped based on shared risk characteristics. This enables analysts to design portfolios tailored to various risk tolerances, optimizing the balance between risk and reward. DBS-CAN. DBS-CAN is a powerful algorithm designed for datasets with complex, nonlinear patterns and noise. Unlike K-means, DBS-CAN doesn't require the number of clusters to be predefined. Instead, it uses two parameters: epsilon, the minimum distance between points in a cluster, and min points, the minimum number of points required to form a cluster. DBS-CAN's strength lies in its ability to find clusters of arbitrary shapes while effectively identifying and excluding outliers. For example, in a financial context, DBS-CAN can be used to detect unusual transactions in large datasets, helping to identify potential fraud. By flagging suspicious activity, DBS-CAN enhances the security and efficiency of financial systems. Additionally, DBS-CAN excels in spatial data analysis, such as geographic information systems, GIS, where patterns in location-based data can be complex and irregular. Its ability to handle noise and identify meaningful clusters makes it ideal for real-world datasets, where outliers and anomalies are common. Principal component analysis, PCA, dimensionality reduction for simplified data. While clustering algorithms group data based on similarity, principal component analysis, PCA, is a technique focused on reducing the dimensionality of complex datasets. PCA identifies the most important features in a dataset and creates new variables, called principal components, that capture the most variance in the data. This technique is especially valuable when dealing with large, high-dimensional datasets, as it simplifies the data while retaining most of the essential information. PCA works by finding new axes in the dataset along which the variance is maximized. The first principal component captures the highest variance, while the second captures the next highest, and so on. By reorienting the data along these new axes, PCA reduces the number of variables and simplifies the analysis. In finance, PCA has many applications, particularly in portfolio management and risk assessment. By identifying the principal components that drive asset returns, analysts can create more diversified portfolios, balance risk, and improve performance. Additionally, PCA is useful in algorithmic trading, where reducing the dimensionality of datasets allows for faster, more accurate decision-making. Fraud detection is another area where PCA shines. By reducing transaction data into its principal components, anomalies and outliers, potential indicators of fraudulent behavior are more easily detected. This enhances the accuracy and speed of fraud detection systems, allowing financial institutions to respond quickly to suspicious activity. Association rule mining. Association rule mining is a data mining technique used to uncover relationships between items in large datasets. It is widely known for its role in market basket analysis, where it identifies items frequently purchased together. However, its applications extend beyond retail and are particularly useful in finance, where it helps reveal complex correlations and patterns in financial transactions. At the core of association rule mining is the task of finding sets of items or events that commonly occur together in transactional databases. These relationships are expressed as rules, evaluated using metrics such as support, confidence, and lift. Support: the frequency with which an item set appears in the dataset. Confidence: the likelihood that the presence of one item leads to the presence of another. Lift: the ratio of confidence to the expected confidence, assuming the items were independent. In finance, association rule mining is valuable for analyzing investment behaviors, detecting fraud, and optimizing trading strategies. By identifying patterns in transactional data, financial analysts can better understand customer preferences, such as which financial products are often purchased together. This helps institutions tailor their offerings and improve customer satisfaction. Association rule mining is also instrumental in fraud detection. By analyzing historical transaction data, it can uncover deviations from normal purchasing behavior, flagging potential fraud. Similarly, in risk management, association rule mining helps financial institutions identify patterns associated with loan defaults, allowing them to adjust lending strategies accordingly. Coders. Autoencoders are a form of neural network designed for dimensionality reduction, especially in large datasets common in finance. The architecture of an autoencoder consists of two main parts, the encoder and the decoder. The encoder compresses the input data into a lower dimensional form, while the decoder reconstructs the data from this compressed form. The goal is to preserve the most important information during compression and ensure the reconstruction is as close to the original as possible. In finance, autoencoders are particularly useful for fraud detection. By training the network on typical transaction data, an autoencoder can detect anomalies, transactions that cannot be accurately reconstructed, flagging them as potential fraud. This ability to isolate unusual data points makes autoencoders invaluable in ensuring the security of financial systems. Autoencoders are also useful in predictive modeling, simplifying complex datasets to improve the efficiency of algorithms used to predict loan defaults, stock prices, and other financial metrics. By reducing the number of variables, autoencoders make it easier for models to focus on the most critical data, enhancing both speed and accuracy. Unsupervised learning techniques such as clustering algorithms, PCA, association rule mining, and autoencoders are powerful tools for analyzing complex datasets. Each method has its unique strengths and applications, particularly in finance, where data-driven decision-making is critical. Whether it's segmenting customers, detecting fraud, or simplifying large datasets, these techniques help businesses uncover valuable insights, optimize strategies, and stay competitive in a data-driven world. As the volume and complexity of data continue to grow, the importance of unsupervised learning techniques will only increase, driving innovation across industries.